somewhere between 23 to 42% of a developer's time is wasted dealing with the consequences of technical debt or bad code in general. 42%. That's a lot of waste, isn't it? Let's take on our business hat and see what would that mean to me as a business manager. It would simply mean that with 42% waste, if I have 100 developers in my organization, it means I pay salaries from 100 developers, but with 42% waste, I'm getting the equivalent output of just 58 people. I'm not a business manager myself, but does that sound like a good deal to you? No, it's disastrous, of course. And in reality, the waste is even larger. And to understand what type of waste that is, we need to talk about this. We need to talk about teamwork a little bit. So before I do this, let me ask you, how many of you develop software as part of a team? So that's like virtually all of you, a few that don't. All right, how many of you have been part of a team building exercise? Yeah, it's same numbers, right? We've all done that. And we all know the benefits of team building. We know the benefits of being on a team, right? Teams are great. But this will be different. This will be more like an anti-team building exercise. Because like all great things, there's also a trade-off. Nothing is ever free, and it's the same for teamwork. It always comes with a cost. And that cost is something that social psychologists refer to as process loss. And process loss in turn is a term that social psychologists have stolen from the field of mechanics. And the idea is that just like a machine cannot operate at 100% efficiency all the time due to things like friction and heat loss, neither can a team. And let me walk you through the model. So let's say we have a number of individuals. Together, they have a potential productivity. However, that's never, ever what we get out of a team. The actual productivity is always smaller, and part of the potential is simply lost. The type of loss depends on the task that we do, but for complex interdependent tasks like software, a lot of that process loss is simply due to coordination and communication overhead. And what that means in the context of technical debt is that, if we waste 42% of developers' times, we can never make up for that. We can never compensate for that by hiring even more people because the process loss increases non-linearly, right? So at some point, each individual that we add is actually going to cost us more. So the more we can do with the smaller team, the better we are. So that means we simply need to start managing technical debt. And given those numbers I've shown you now, and given what I explained about process loss, and given the fact that there's a global shortage of software developers, right? So I'm from Sweden. Sweden is a really small country, but even in small Sweden, we have an estimated shortage of 60,000 developers over the next 2 years. And no one knows where to find them because it's a global shortage, right? So if we have a global shortage of software developers, does it make sense to you that we waste 42% of their time? You would expect technical debt to be really high on any decision maker's agenda, which is, of course, not at all what's happening in reality. Because the research constantly finds that many businesses keep forcing developers to take on new technical debt as we hunt for the next feature that we need to deliver, the next urgent thing. So why is this happening? Why aren't we doing a better job at managing technical debt? I think I know why, and I would like to explain why that happens. And to explain why, we need to look at some laws of software evolution. We need to look at what happens when we build code. And the first law of software evolution is the law of continuing change. And the law of continuing change simply says that the system has to continuously evolve and adapt, or it will become progressively less useful over time. Is this something you recognize? Yeah. This is the very reason why we keep adding new stuff, why we keep adding new features to existing products, because a successful product is never done. What I want you to do now is to notice that there is some tension, some kind of conflict to the second law of software evolution. And that's the law of increasing complexity. And this law says that when we evolve our systems, their complexity will increase unless we actively try to reduce it, right? So that's what's happening when we take on technical debt. The complexity increases, which in turn makes it harder and harder to respond to change. If we take an outside perspective and look at these two laws together, you will see that there's a difference in feedback timing. When we do a new feature, we get very quick and immediate feedback the moment we put it in the hands of a user. Whereas for increasing complexity, the feedback timing is much, much longer, right? This is something that happens over time. And this difference in feedback timing is like an open invitation to something that psychologists know as a decision-making bias of hyperbolic discounting. So has anyone heard about hyperbolic discounting before? One of you. Cool, I got something new for you. So hyperbolic discounting is a decision-making bias where our current self makes decisions that our future self is going to regret. Hyperbolic discounting is frequently used in the psychology of addiction to explain substance abuse and addiction. It's also, coincidentally, the best description I know of why companies fail to manage technical debt. Because companies, just like the addict, is lured in by the promise of the next quick fix, the next immediate reward. Right? Delivering and pushing those features out that seem urgent, and we do that at the expense of a long-term well-being, which in terms of software means a maintainable and sustainable code base. To fight hyperbolic discounting, it's really, really important to visualize the potential consequences. Because if we can visualize the potential consequences, then we can also prime decision makers to start thinking about the future, which makes it so much more likely that they will actually act now. So how can we visualize accidental code complexity and technical debt? Software kind of lacks visibility. Well, let me take you on a tour and see if we can get there. First of all, when talking about complicated code, we have to understand that it's really, really hard to measure that. And I've taken a lot of inspiration from this paper. And this paper in the first paragraph basically tells us that if we look for a single number, single metric, to capture a multifaceted concept like code quality or code complexity, then we are doomed. There is no such thing. Software is way too complicated. What I've done instead is that I've taken a lot of inspiration from the second paragraph that says that the most promising approach is to identify specific attributes of complexity, measure them separately. And I've been calling this concept code health. It's something I've been working on over the past 5 years. And the idea with code health is that we define properties that we know from research that they lead to increased maintenance costs. They make the code harder to understand. And I'm going to show you some examples in just 30 seconds. We then measure these things separately. So in the current code health concept, I have 25 different factors that I measure. We measure them separately, we aggregate them, we normalize them, and we can then categorize every single piece of code in a system as being in one of 3 different categories. So we have each one of those bubbles. We're going to look more at the visualization soon, but each one of those bubbles represents a file with code. Everything that's green, that means perfectly healthy code. No code smells, no particular complexity issues. Everything that's yellow, that's the warning space. So this is where we start to take on increasing complexity. This is where we have technical debt. And finally, unless we're careful, we end up in the red category. And red code, as you will see soon, is disastrous to any business. Now, to give you an idea on what we measure in a code health concept, we look at typical module level smells, things like low cohesion. So low cohesion is when you have a module and it includes way too many responsibilities. So you have stuffed too many features into that module. And that in turn makes the code very hard to understand because you need to understand all this concept. And it also puts you at risk for things like unexpected feature interactions, right? Then we have things like brain classes, which is a module with low cohesion that also contains a brain method. And the brain methods are a function level smell. So brain method is this, they're typically very large functions. They're overly complicated, lots of conditional logic. And that method also tends to be very central to the module, meaning that each time you go into the code to make a change to that module, you end up in the brain method. And they typically grow more and more complicated over time. We include classics, like my dear old friend, copy-paste, right? We include different code complexity patterns. In particular, one thing that we have found has a huge impact on code health is what's called deeply nested logic. So deeply nested logic is when you have an if statement, then you have another if statement inside it, another if statement, and then maybe a for loop for good measure, right? So your code looks kind of like an arrow, right? The reason deeply nested logic is problematic is because it puts a huge load on our cognitive memory, and there's some very good research that suggests that. And I want to show you how it can look. Here's a code health visualization from a large code base. This is Ethereum on open source blockchain implementation. The code you see there is roughly 600,000 lines of code. It's visualized from 50 different Git repositories. And the way it works is that if you see those circles that I'm hovering over right now, each one of those represents a top-level folder, right? So this is a structure that always follows the code. So I can quickly say that there's a package called research, and I do see some red code there. I can then zoom in, since this is interactive, and dive down to any level of detail I'm interested in. And then once I get to the lowest level of detail, I see that each file with source code is represented as a circle. The size of a circle just reflects the number of lines of code. So the larger the circle, the more lines of code in that module. And the color represents the code health, the three categories. I'm a big fan of visualizations because visualizations kind of tap into one of the most powerful pattern detectors that we have in the known universe. The human brain, right? So it makes it very, very easy for a business. If we can visualize code health like this, then we can very quickly decide, do we have any problems? If yes, where are they and how deep do they go? And to give you an example, I have two different code bases here. The first one is React, a UI library developed at Facebook. And we see here that, yes, indeed, there is some red code. There's a cluster of red code. And that cluster is in a component called React Reconciler. So I'm going to tell you how to act upon that data later, but we immediately see that it seems to be a local problem. And we can contrast that to Core CLR that you have to your left, or to your right. And you see that Core CLR, that's a runtime for .NET from Microsoft. And you see it's a really, really large code base, 8.5 million lines of code that you see on screen. And if you look at the red parts of it, I mean, it looks like, you know, a bacteria culture gone mad, doesn't it? There's a lot of red code there. And this is going to be really, really expensive to act on. So what I want to show you towards the end of this presentation is how do we deal with code bases that look like this. Before we go there, we need to understand if these different code health categories, if they actually mean something from a business perspective. Because without a business connection, all of these are just vanity metrics. So me and our colleagues set out to quantify the business impacts of complex code. And the way we did it was that we collected data from 39 commercial code bases, so real-world code bases under active development at 39 different companies. Data analytics, infrastructure, networking, all kinds of domains, because we wanted to make sure that whatever we find, it's possible to generalize across businesses. And for the same reason, we included code in 14 different programming languages to make sure that what we find isn't specific to a certain language, it generalizes. And by the way, everything that I'm going to show you is statistically significant, meaning that it's not just a fluke. There's some real data, a real signal in the data. All right, so how do we do this? How do we find the business impact? Well, what we decided to do was to measure the time in development. So does it take longer to develop a feature in red code versus green code? The main problem with that is that no organizations actually know their development costs. They don't know how long time they spend in development. And this kind of sounds like a really strange statement, because of course we know how much time we spend in development. But so let me explain what I mean. As a manager, we know what our staffing costs are. So I know if I have 10 developers, this is the salary I pay them. I could also, via some Jira magic, I could figure out roughly how those costs are distributed across different Jira tickets, right? So I could kind of calculate that we spent these many hours on this particular feature. But we previously had no way, really no way, of knowing how those costs are distributed across potentially thousands of modules in our code base of various qualities. We never had that level of detail. So this was the first challenge that we kind of needed to attack. And we did that by using the following algorithm. What happens now is that we piece together data from Jira and Git. So basically, for every single feature, every single Jira card, we start the clock for time in development the moment we as a developer pull a card into an in-progress state. So that's where we start the clock. And then at some point, we make a commit and we reference that Jira issue, so we pass the clock. Now, if the feature is done at this stage, then the cycle time between ticket moving to in progress until the first commit, that's the time in development for that Jira issue, right? But sometimes we do more commits, we do multiple commits. And if that happens, then we calculate the cycle time from the previous commit to this commit for different files. And we might even do a third commit. And at the end, we simply sum up these different subcycle times. So we get like a time in development per file per Jira issue. Did I manage to explain that? Good, very good. So now, we had a data set that included the code health for every single file, the time in development for every single file, and since we're using Jira, we could also figure out how many bug fixes have we done in each one of the files. So we can finally answer this question: does code quality matter? And this is a question I wanted to answer for decades, because I've spent 25 years in the software industry, and during those 25 years, I have more or less learned that everyone knows, really knows, that code quality is important, yet no one ever had any data to support that statement. So to me, it's about moving from knows that code quality is important to actually knowing by showing data. So, what did we find? Does code quality matter? Yes, it does. The first thing I want to show you here is the average time in development depending on code quality. And what we see here is that if I implement a feature or fix a bug in red code, then that takes more than twice as long as making a change to green code. So what does this actually mean? Well, to a decision maker, what this means is that if it took us, my team, 2.5 weeks to implement a specific feature, and our code is red, then our competitors that have a green code base, they could get the same feature in less than 1 week. So this is very much about speed to market. This is really, really important. But I have to admit that this result didn't really surprise me, because this was pretty much what I would have expected given my years in software. But what did surprise me was the next research question that we looked into. So now we wanted to look into something that we call the uncertainty in completion time for different features. And what we did differently here is that instead of calculating the average time spent in development, we looked at the maximum time in development for every single file, right? And what these results show is that green code seems to be very predictable in the sense that the maximum time it takes to implement a feature is very, very close to the mean time, meaning there is low variability in green code. So it seems that green code is predictable. I will know roughly how long it takes to make a change to green code. Whereas we see that for red code, that relationship is no longer true. Because in red code, the maximum time it can take you to implement a feature can be an order of magnitude larger. What does this mean to us as an organization, as a business? Well, to me, it means uncertainty. I'm currently working as a CTO, and I have to admit that as a CTO, I strongly dislike uncertainty. And I dislike uncertainty because it makes me look bad, right? So let's, for example, say that I promise you that, we're going to have this new feature in a month, but our code is red, so it actually takes 9 months to implement that feature. You're going to get really upset, right? If I instead take on my developer hat, then I also strongly dislike uncertainty, because uncertainty is what's causing me stress, overtime, and missed deadlines. So no one likes uncertainty, and red code seems to be like a receipt to introduce uncertainty. Finally, the last data set I want to show you is that we also looked at the correctness perspective. So here we looked at, okay, what's the distribution of bugs, of defects, across code of various qualities? And what we see here is that red code has, on average, 15 times more defects than green code. And this is important because this pretty much comes down to customer satisfaction and the product maturity experience. Now, the stuff I've talked about is very easy to see how it kind of relates to the business side of software, how it's important to a business manager or a technical manager. But is it important to us as developers? I mean, after all, you could say that, if a business chooses to waste 42% of our time on technical debt, then maybe that's a good thing for us, because it means that we will get even more in demand, right? That's job security at its finest, isn't it? We can even drive for higher salary. No, trust me on this one. Technical debt is not good for you. And the reason I can say that with confidence is because I read this wonderful book that I highly recommend. It's a collection of research papers. And there's one study in particular that I find truly fascinating. So this is a study that looked at the happiness of software developers. And happiness, that sounds like those warm, fluffy concepts. But it's actually possible to measure that. There's a standardized scale within psychology that you can use. You can get some very accurate numbers. And it's a large-scale study. They studied 1,300 developers, and more specifically, they looked at what makes a developer unhappy. And an unhappy developer is also a developer that has a lower productivity. So this is important both for well-being and the financial aspect. And there were 3 things that stood out in particular. The first was that we developers, we really, really we become very unhappy when we get stuck in problem solving. Right? Does anyone recognize that? I definitely do. You know how frustrating it can be. You have this particular bug and you think that, I can fix this in 5 minutes, right? Then you dive into the code and you start to fix it and something else breaks and you try to fix that and something else breaks and you end up spending 2 weeks trying to fix that bug, right? That's extremely frustrating. And that's very likely to be the case with red code, because remember, red code had that extreme unpredictability, right? Things can take an order of magnitude longer, and that's most likely reflecting being stuck in problem solving. It's also very easy to see how low code quality can lead us to the second thing, time pressure, right? Because if we think something takes 1 week and it ends up taking 9 weeks, then of course the whole organization is going to get under time pressure. And finally, the last quote, I really like it. There's this wonderful quote that we developers, we suffer tremendously when we meet bad code that could have been avoided in the first place. And that's kind of the textbook definition of technical debt. Now, a number of use cases for you. Given all this data that we have seen on the costs of code quality and the business impact, how do we use it? How do we integrate it in our daily work? There are a number of things I have seen works really well. One of them is that if we know the code quality of every single piece of code that we have, then we can also make sure that all stakeholders, not only we developers, but also our managers and the product, have a shared understanding. Because once everyone has a shared understanding, that becomes possible to fight decision-making biases like hyperbolic discounting, right? We know that this part of the code is red. We have to be really, really careful here. Finally, what I like as a developer with this is that I can now actually build a business case for larger improvements and large-scale refactorings. So I can actually say that, okay, yeah, you want us to work with this part of the code, it's red, it means a lot of uncertainty, development would take longer, higher risk for bugs. But if I refactor it to become green, I know that we're very likely to be at least twice as quick the next time we need to implement a feature there. So we can actually make the business case, which makes it so much more likely that the business people will listen to us. So it's one way for us to let business people peek into our otherwise inaccessible world of code and code quality. And to show you a specific use case, so this is something I've been using a lot with different teams. And this is an example from another code base that we haven't seen before. This is a code base called Erlang OTP. So Erlang OTP is a programming language and a runtime system developed by Ericsson. It's open source since many years, which is why I can show you this. Now, let's pretend that we together, we work in the same team, and we sit down in a planning meeting. We want to do a couple of new features. Now, in a planning meeting, one of the most interesting things you can do is to just visualize your code quality, like this. I'm going to show you some tooling examples soon. Because the moment I do that, we can have an informed discussion together with the product people. So let's say that the product people, they push ahead for a new feature in that part of the code called megaco, the one with the circle around. We immediately see that there's a lot of red and yellow code there. So this will be a huge risk. We can, of course, choose to go ahead with that feature anyway. The difference is that we are now aware of the risk so that we can actually plan for it, because we know there is a huge uncertainty in any guesstimate we come up with. Or we could say that there's another feature that's equally important. There's another feature we can do there in this package called diameter. And we see in diameter, all code is green. So this is likely to be much quicker and much more predictable. So let's go ahead with that feature instead. Or, in the best of all worlds, we go back to a drawing board and says, okay, let's use this as motivation to actually refactor the code in megaco. So in the future, we can go ahead and implement new features there with lower uncertainty and a higher predictability. So there's one more thing I wanted to show you that's highly related to technical debt. Because to me, finding bad code is actually the easy part of technical debt. Because trust me, there's so much bad code out there. A much, much harder problem is to prioritize it. Where do we actually start? And we could, of course, go ahead like this and prioritize based on where we plan to work with features. But sometimes we want to be proactive and actually start to refactor our red code. So how do we do that? Let's return to this case study I showed you earlier, the Petri dish, that is core CLR, 8.5 million lines of code. You see all that red code. The first thing I do when I come across a code base of that scale with so much red code is that I switch perspective and I use something called hotspots. So hotspots, it's the same type of visualization. It means the same thing. Each circle is still a file, but the colors carry a different meaning because the colors now reflect the change frequency of the code. So what is change frequency? Well, change frequency is data that we can pull out of our Git repositories. We simply go to Git, and for every single file, we look at how many times have we made a commit, how many times have we made a change to that particular file. And we sum that up and visualize it using color. So the more red something is, the higher the development activity. It's a development hotspot. All right? Are you following? Perfect. Cool. Now, what's so fascinating with hotspots is that most of our code tends to be very stable. So remember, 8.5 million lines of code, and we see that the majority of it is very, very stable. And from a technical debt perspective, this means that this is code with a low interest. So this is basically like a free loan, right? We still want to know about it, but because of future risk. But it's unlikely to be an immediate concern. It's unlikely to be urgent. So that's the part of the code where we can live with red code. On the other hand, we see that the hotspots, they make up a pretty small part of the code base. We see a cluster of hotspots there in a package called GIT, the just-in-time compilation module in CoreCLR. And these hotspots are really, really important because any technical debt that we have there will be high interest debt. Due to the high change frequency, even a minor amount of code alpha issues can quickly become extremely expensive. So we want to make sure that the hotspots, those are our refactoring targets. However, when we start to look deeper at this GIT package, we see that some of the hotspots, they are really large files. The top hotspot here is something called gentry.cpp, and it's a C++ file with 14,000 lines of code. That's quite a lot, isn't it? Let's have a look at that code. Here's a small snippet. Now imagine 14,000 lines of code like that. I have to tell you that I used to be a C++ developer. I did C++ for 10 years. I know, 10 years and never get back, right? But what it also means is that I have a lot of respect for 14,000 lines of C++ that looks like this. There's no way we're ever going to be able to refactor that. And if we try to, we branch out and we work on it for 6 months trying to clean up that code. At the end, we're never going to be able to merge that branch because remember, it's a hotspot, meaning it's under active development. So in the meantime, our colleagues have made changes and new features to it, right? So this is clearly not actionable. So we need to do something else. And that something else is what I call an X-ray. So when I come across a large module like this, what I do is I take the file and I parse it into separate functions. Then I look at the Git log and I see where do each commit hit over time, and I sum it up so that I get hotspots at the function level. And this is what I use to get a prioritized list of refactoring targets. Let's have a look at the X-ray of gentry.cpp, this massive C++ file. We see that the number one hotspot at the function level is a function called gt_clone_expression. And we see in the first column that it has been modified 42 times. That's the change frequency. Right? So lots of modification to that module. We also see in the last column to the right, a column called cyclomatic complexity, 112. Does anyone know what cyclomatic complexity is? Some of you, cool. So cyclomatic complexity is one of these really classic complexity metrics, right? From 1976. And the way that metric works is that you calculate the number of branches in a function. So each time you have an if statement, +1. Each time you have a loop, +1, and then you sum it up. Do you know what the thresholds are? The thresholds for very high complexity, the point where it's a real concern, is defined to be 15. Right? So 15 logical statements, 15 branching points. Here we have 112. So that seems to be quite complicated. The reason I use cyclomatic complexity in an X-ray is because I find that cyclomatic complexity has some very good predictive power of one aspect. And that is how many unit tests I will need to cover just that function. So what this data tells me is that if I want to write unit tests for gt_clone_expression, I need at least 112 of them. So that kind of tells something about the complexity of that module, that function. We also see in the lines of code column that we have roughly 500 lines of code. That's a lot for a single function, isn't it? It is. But 500 lines of code is much less than 14,000 lines of code, which was the size of a total file. And 500 lines of code is definitely less than 8.5 million lines of code, which was the size of a total system. So even more importantly, I am now at the level where I can do a focused refactoring based on data from how we, as an organization, have worked with the code. And even better, that refactoring can come with a business expectation. So I've come to the end of this presentation, and I'm going to leave a couple of minutes for questions. But before I do that, I'd like to sum it up for you. Because during my 25 years in the software development, I had so many people tell me that, no, we don't have time for this. We don't have time to do the design properly. We don't have time to write unit tests. We don't have time for refactorings. But what this data suggests that we saw today is that there really is no such trade-off. Actually, the contrary seems to be true. It seems that if we really want to go fast, we also need to go well. Because what we saw in the data was that low code quality, it actually leads to more than twice as long development cycles. You know, an unpredictability where things can take an order of magnitude longer and 15 times more defects. So the business impact of code quality should be unmistakably clear. And I also wanted to show you how you can add hotspots on top of that to actually make those findings actionable and prioritize the quick wins in your code base. And if you want to try this on your own code, the tool I've been using for both the study and for the visualizations is CodeSyn. You have a link there. There's a free community edition of CodeSyn, free forever. And if you have proprietary code bases and you would like to find out what's my code health, then you can run CodeSyn for free for a month on any proprietary code base. So please try it out and see, does this bring additional value to me? What kind of health do I have in my code? If you want to know more about the actual analyses, then I've written a whole book about it called Software Design X-Rays, where I cover all these techniques and many, many more. I blog regularly about this at codesyn.com, where you can find a blog and a white paper that sums up the main points of the Code Red study. And I blog occasionally at adamtornhill.com. Now, I'm going to hang out the whole day, so please grab me if you want to discuss this or you want to discuss software in general. I love to talk, so please come up to me. And before I take questions, I would like to take this opportunity and say thanks a lot for showing up at my session. I really, really appreciate it. And may the code be with you. Thank you. Please raise your arm if you want to ask a question. We have a microphone here somewhere.
Hello. From a research point of view, you have some code that you may not reach production. And I'm interested in what's the difference between time of implementing red code or green code?
Yeah, so the difference, I think the average difference is that it's 2.4 times. It takes 2.4 times longer in red code compared to green code. But what's important is that there's an impact already in yellow code, where it's almost twice as long already there. So we seem to take a hit the moment our code quality starts to drop. It doesn't have to go disastrous for it being expensive to us.
Thank you.
Thank you. Any other questions? There's a question over here. And by the way, all these findings, the research findings, they are available online. You just Google Code Red, Adam Tornhill, and you will find a research paper, and you'll find a white paper that could be more accessible if you want to share it with your management.
Yep. So I have a question about the proof of concept applications. Should it matter to write clean code or not? Because the code may reach production or not, and maybe if application becomes a real application, that code can be cannot be used.
Yeah. So to me, there are. I work. Part of my work is working with research. So this is code where I just want to prototype something, try something out. I never write bad code just because I can, but I obviously know that I shouldn't spend way too much time polishing this. as long as I really know, that this code is going to be thrown away. If I'm in doubt that this code might actually be used in production, then I really recommend to pay a lot of attention to it. The thing is that we will never, ever get code right the first time, right? It's always an iterative process. And I think it's very, very important that when we work with code, we make sure that we don't slip in quality. That said, there are situations, because this is always a trade-off, there are situations where we might choose to take on technical debt, the prudent technical debt, and say that, okay, we really have to deliver this thing next week, otherwise we're out of business, right? We need to do this. If we're out of business, it doesn't matter that the code is green. So what we can do now is that we can choose to take on technical debt and do a shortcut, squeeze something in, make a code worse. The very important thing is that if we know the quality of a code, if we have that visualized, then we can know where we can safely take on technical debt and where we cannot safely take on technical debt because it's too unpredictable. So having that shared understanding is, to me, key to be able to doing these trade-offs. So I hope I managed to answer your question. Thank you. Do we have time for more questions? Ah, perfect. Please go ahead.
Hello.
Hi.
First of all, great presentation. Thank you for that. I'm personally curious whether or not you had scenarios where the hotspots that you identified didn't actually cover the core issue of the bad health. I'm thinking of a module that is poorly implemented and forces other areas to be more oftenly worked upon.
Yes, very, very interesting. So there are a number of things with hotspots. So hotspots are about relevance, never quality. So hotspots just tell us that this part of the code is more important than this part of the code, in the sense that we do more work here, right? So in some code bases, you find that all your hotspots are green code. And when that happens, then you're in a very, very good position, because it means the code you work on the most also has the highest quality. This is really important. This is where you want to be. Then in other scenarios, you might find that the main problem with this code base isn't necessarily that each module is overly complicated, because we also have this different type of complexity, where the complexity still exists, but now it's distributed instead. It's in how the different pieces connect to each other. So we have strong dependencies, unexpected dependencies. And there is a behavior code analysis technique. I have covered it in other talks, and there are a couple of them are on YouTube. I also have, I think, 2 chapters in Software Design X-Rays on this technique. It's called change coupling. It's a behavioral code analysis technique where you basically trace the patterns of how the code grow. So if I modify the code over here, I also have to make modification here, here, and here. And you can kind of calculate those patterns and traces over time and see some very clear trend, meaning that you can also visualize the logical and implicit dependencies in your code. So this is another aspect that I'm using all the time myself as a complement to hotspots and code health. Did I manage to answer the question? All right. Please catch me after the talk or catch me at the after party. And once again, thank you everyone. Enjoy the rest of the day.